Okay. So contest 342. I feel like this one was not the most difficult. Like problem 5 was a medium, or problem 4, and so is problem 3, and then the first two were easies. Um, Plus, like the rate limiting was this huge equalizer. Like if you look at people's rankings, like it took them a minute to do the first one. For oh no, that was me. All right, it took this person like 30 seconds to do the first one, and when we look at the first one, it'll still be like that's pretty bad. Like 3 minutes for the third place in the world. So clearly, like some people got screwed over by rate limiting, which helped me a lot. So the first one, people on YouTube can pause to read it, but the idea is just we have an arrival time and a delay time, and we want to know uh, when the train will arrive. So it's pretty much just return the sum modulo 24. So it's just like add them together, and then if it goes past 24, say it goes to 25, then they arrived at 1 a.m. So like return 1. Uh, this one's pretty basic. I think the only real thing to learn is just like actually these problems do pose a useful lesson, which is like this is a one-liner, and when I first wrote this, like for me it took me a minute. That was my time on this one, and I think I wrote this out probably in 10 seconds and then spent 50 seconds thinking like, is there a corner case I'm not accounting for? This seems way too easy. What's going on? But it really is just that easy, and there's no corner cases. So I think I like ran a couple test cases, and that's probably good to do, but for me, for the future, just like not even spending that much time thinking about it and just being confident. These problems kind of cause you to, they force you to like run through exact steps of the code and think about exact corner cases and exactly what the code's going to do. And that's a really useful skill even for a lot harder problems. But when all is said and done, that one's very easy. Some multiples. This one's also quite easy. This one's just like you can see that n can only go up to 1,000. So you can just count through every number because you can easily iterate up to 1,000. So you just iterate up to 1,000 and you add every number that's divisible by 3, 5, or 7. And then the only thing, this was the huge gotcha here, was can't have 0, and you got to go up to n plus 1 because it's 1 to n inclusive, and they even bold it. This is the kind of thing that probably costed a lot of people 5 minutes. Like we can see almost every single person that tried this had it accepted, but there's like a bunch of people, there's like 2,000 people that tried it, failed, and then got it accepted the second time. Probably what they did was they just said for I in range n, or for I in range n, or I in range 1 n, or something like that. But yeah, once again, another problem that's trivially easy as far as these contests are concerned. But the danger here is either that you spend too much time second guessing how simple it is, or also that you don't catch these slight little +1 things. Okay, sliding subarray beauty. This one's a lot more interesting and difficult. So we go through, we take like a little subarray snapshot, and we say what's the kth or the xth smallest integer, or 0 if the xth smallest integer is not negative. So this is perfect for a multi-set or a sorted list, which is basically it's an ordered list. It's a sorted list. And we can access, we can add, we can remove all elements in O of log n time, which is perfect. Because n is 10 to the 5th, so this will wind up being n log n if we have to iterate through with this sorted list. Or really, it's actually n log k, because the sorted list is never going to grow beyond the size of k. But even still, basically n log n. So what do? We go through, we add everything into the sorted list, and the sorted list under the hood is like a tree structure. So when we have this, we can find an element by its index. We can find an index by its element. And we use those. We can add and remove things. So we add everything. That's the initial k length. So we start and we say like add 1, -1, and -3 when k is 3. And then we say x is 2. So we want the second smallest integer, which should be -1. And that's something that's important, is that we don't want like the 0th, 1st, 2nd smallest integer 0 indexed. We want the 2nd smallest integer 1 indexed. And that's actually where my bug came from. Was I was like, oh, this is x minus 1, but this, I still had x, and that screwed it up. But that's why we use x minus 1, because the 2nd smallest integer is really the 1st smallest 0 indexed. So we want like the 1st index in the tree map, or the multi-set, or the sorted list. So add everything in, and then I just do the sliding window. So I say, okay, add in the x's smallest integer, or the x minus 1th if you're doing 0 indexed, and then remove, the 1 and add the -2, and then remove the -1 and add the 3. And so on. And then at the very end, you see this a lot with these sliding window problems. We either need to have something at the beginning that's like res.append this current state, where the sliding window is this, and then we can go through and we can add this and add this. Or the way that I had it here, the first thing we do is res.append, and then we change to update the state. And then we're going to have at the end the final state that we append. So you're always going to have some sort of like res.append. You're going to have one of them outside the loop, whether that's before or after. That's kind of a personal preference. Yeah, so we roll through the tree map. And there's a lot of problems where you roll through with a tree map. This is quite common, like sliding window medium, sliding window maximum, sliding window minimum. Anytime you see sliding subarray or sliding window, I mean, that's a dead giveaway as far as the approach they want you to use. But beyond that, there's a very good chance that you're going to use a sorted list or a tree map or some sort of like sorted data structure. Yeah, a lot of those problems you can do better than n log n. Like sliding window maximum, you can do it in O of n if you use a monotonic stack, but you can get away with a sorted list. And in this situation where you're not trying to prove the best O of n time complexity, like in a job interview setting, you might as well just use log n, because at the end of the day, log n is basically O of 1. If you think of like the total amount of atoms in the universe, that's not useful. 10 to the 57. So then if we say log base 2, yeah, I've already Googled this one, we get 189. So the largest conceivable number in the physical universe that you could really get, log base 2 of that is less than 200. So like if your O of 1 constant was 200, then n log n would be less than O of 1. So the point of that is to say log n is basically O of 1 for these calculations. And also the takeaway is learn these like sorted data structures. So sorted list or multi-set, tree map or sorted dict in Python is what that's called. Sorted set. There's a couple of other ones, like a hash multi-set or a multi-map as well. And a lot of them, you sort of get this like, hey, why can you append and pop from a vector in O of 1 time or a list in O of 1 time? And then the answer is like more confusing than you would think. These have a lot of that. These are like how this works under the surface is pretty actually potentially confusing for some of these data structures, but you don't really need to know that. You just need to know the time complexity for each of these and like when you would want to use them. Okay, so the most interesting one, minimum number of operations to make all array elements equal to 1. So we can take any two adjacent numbers in the array and set one of them to the greatest common denominator between the two. So for example, 2 and 6, we could set the 6 to a 2. Or we could set the 2 to a 2, but we would never want to do that because then you're not changing anything. And we want to know the minimum number of steps to make everything be 1. Or if we can't make everything be 1, then return -1. So in this situation, we can't make everything be 1 because the greatest common denominator between all elements in the entire array is 2. Everything's divisible by 2. So we can make everything 2, but we're never going to get below that. Here we can. We could say, like, set the 6 to be a 2, and then set the 2 that the 6 became to be a 1, because GCD between 2 and 3 is 1. set this 2 to be a 1, set this 3 to be a 1, set this 4 to be a 1. Or we could do it even faster and just say between 3 and 4, set the 4 to be a 1, set the 3 to be a 1, set the 6 to be a 1, set the 2 to be a 1. Yeah, so, and we can surmise a couple of things immediately from that. So the first thing to look at is like 6, 2, 3. I actually wrote out like 3, 15, 5, because I was thinking like, what's a situation where you would ever want to run a GCD between one number and one side and then one number and the other side? So if we take 3, 15, and 5, like these all have a GCD of not 1. Like the GCD here is 3 and the GCD here is 5. So are we just screwed, or what happens here? How do we optimally do this? Well, we never really want to change the 5. We never really want to change the 3. And even though the 15 has isn't relatively prime to either of these, we could set it to be 5 if we took this, and then set it to be 1 if we took that. Or the other way, we could set the 15 to be a 3 if we took this, and then a 1 if we took that. And that tells us something. That tells us that if there's a number that is not relatively prime to either side, and I'm just running through my thought process for this problem because I could just go over the exact solution, but I think going over the thought process is more useful. But it's not relatively prime to either side, but then either side is relatively prime to the other side. Then we can get this down to a 1. But then the problem is, you could imagine that this is like, let's say 75, and then this is like 50, and then after that is like let's say this is 75, this is 75, and this is 5. Yeah, in this situation here, we need to connect both of these. We need to connect this 3 to this 5 because both of them are relatively prime. So in this situation, we have to like set this 75 to a 5, and then set this 75 to a 5, and then set this 5 to a 1. And all this is to say that, like, you know, this is working with the mental Play-Doh of how can we greedily make a decision? Because if we can't do anything like that, if we can't set up any rules, then what we would have to do is just backtrack. And we have to be like, try this. Okay, now that we have a different num state, try this. And now that we have that state, try something else. And then, oh, okay, that either didn't work or it did work and we got some number of steps. Okay, now backtrack and try something else and see how fast that is. And we could save this. We could hash this for like a DP state. Maybe that's a way to do it. But if you're just hard backtracking like that, nums.length is 50. And this is another hint. But 2 to the 50 is not good enough. That's like way too large. And the way that this is a hint is with something like 50, 2 to the 50 is too big. Anything above like 2 to the 25 or 2 to the 30 is going to be too big for O of 2 to the n. But as far as like polynomial time complexity goes, we can just do whatever we want. We could have this be like O of n to the 4th, and it would probably be fine. Or even O of n to the 5th or something. So with that in mind, my thought process when I was working through this problem was like, okay, so then if we do have some array, how do we know the quickest way to get, I mean, everything to 1, right? But how do we know the quickest way to get something to 1? Because the moment you get something to 1, like let's say this was 1, 6, 3, 4, or let's say right here, this was instead of 3, 75, 75, 5, let's say it was just 3, 1, 75, 5. Well, the GCD between 1 and everything else is 1, right? So this will set to 1. This could set to 1, and then this could set to 1. So the moment you have a 1, the solution instantly just becomes the number of other things that's not 1. And that's actually the first thing I do in my code. I think it's unnecessary, but I just say, like, look for the amount of 1s. If there's any amount of 1s, then just return the length of numbers minus the amount of 1s. So let's say you had like 1, 6, 1, 9, 7, 5, 1. I'm zooming in a little far here, but something like this. it doesn't matter where the ones are, nothing matters. You just are like, okay, set this to a one, set this to a one, set this to a one. Do it in any order you want. I mean, you have to make sure that something's adjacent to a one, but it doesn't matter. You're just setting everything to one. So the order doesn't matter the moment there's a one. The moment there's a one, you can just set everything to be one. With that in mind, the question then becomes, is that always optimal? Is there ever any situation where you wouldn't want to first set something to be one? Let's say this is like 76 and 4 and 9 and all this. Is there ever any situation, let's say this is 5, where you wouldn't want to just say, okay, take GCD between 6 and 5, set this to 1, and then the answer just becomes the length of nums minus 1, because you're setting the number of elements minus this thing that's already a 1 to be 1. Is there ever a situation where you wouldn't want to do that? And if you finick around with it for a second, it's kind of like, no. Like, take this. Take if we just have 3 and 4. These are relatively prime. So no matter what, the first thing you have to do is set something to 1, and then everything else to 1. And it's true that if you had, like, let's say 3, 4, 5, 6, you could also say, take GCD here, set the 3 to a 1. Take GCD here, not including any 1s, set the 6 to a 1. Take GCD here, set this to a 1. You could do it by taking other GCDs of things that aren't 1, but it's always at best the same as if you just set something to a 1 and then you went through and changed everything that was adjacent to that to be 1. And it's important to go over this. It seems unrelated, and when I was doing this, it was sort of like I didn't know potentially how this was going to lead to an answer. But this is the kind of thinking, this is the kind of like rule setting that's really important for constructing your way into a solution, like through the vacuum of, I don't really know how to do this. Anyway, with that in mind, then going back to our original thing, let's say we have, again, like 3, 75, 75, 5, or whatever, something like this. How do we know the minimum way to get any one number to be a 1? Because it might be more complicated than we think. It might be like, it's not obvious a greedy solution to make everything 1. And I thought about it for a little bit, and I thought about how, like, the problem is that, like, to set this to be 1, it's predicated on, like, what you could set this to be. But then what you could set this to be, let's say, and I'll make it a little more, like, abstract. We'll say, like, x dot 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 y, something like that. So if we're seeing, like, how do we set this to be a 1? It's like, well, can we set this to be something that's relatively prime to this? And if so, how quickly can we do that? Because say this is like 30 and this is like 50, you know, they're not quite relatively prime. We can't get away with anything there. But say we could, you know, this was right next to a 7. That's a bad example because then we would want to just take these. But say this was right next to a 3, then we could set this to be a 3 and then these would be relatively prime, something like that. But maybe there's a way where this is like, I don't know, say this was also a 30 and then we had a 3 here. Then there becomes all these decisions and it becomes not apparent at all the quickest way to set this to be 1. So my first idea was, okay, say you have some big array, try setting each individual number to be 1. Be like, how quick can I get this number to be a 1? How quick can I get this number to be a 1? How quick can I get this number to be a 1? But as I've just been talking about, even that, it's not very apparent to me how you would do that. And that's when I looked at the like the length of 50 and I went, well, hold on. I don't care at all how quick, like at that point, I could just take every single subarray because that's O of n squared. And the moment I do that, I can recognize this sort of like transitive property here where like the GCD between 2, 6, and 3 is the same thing as the GCD between like 3, 6, and 2. And the GCD between 6 and 3 is the same as the GCD between 3 and 6. I don't know if that's true. I think that's commutative, maybe. I forget. But that's important because that means that like we could just take every subarray and be like, what's the GCD between 2 and 6? 2. Okay, that's not good enough. What about 6 and 3? 3. That's not good enough. And then 2, 6, and 3. Hey, that is good enough. That gets us 1. Okay, cool. So the minimum length subarray we found is 3. we would have to take the GCD between these three elements in order to get a 1, no matter how we did it. We would probably want to take we could set the 6 to a 2 and then the 3 to a 1. We could set the 6 to a 3 and the 2 to a 1. We could set the 6 to a 2 and then take this GCD and set it to be 1. We could do whatever we want, but we know just by looking at these, if we take a rolling GCD, like a prefix sum, but like with GCD, we'll say, okay, GCD between 6 and 2 is 2, and then GCD between 2 and 3 is 1. So then we would get sort of this like mini subarray of like 2, 2, 1 if we're rolling through, and then we would go, cool, we found a 1. And then we don't need to go any further. We don't even need to look at this 4 as far as any subarray starting with 2 goes. We would just say, okay, like we found a subarray of length 3. And then similarly, we would keep going. We'd be like, okay, 6 and 3, GCD is 3. 3 and 4, GCD is 1. So this also works. That doesn't beat our minimum, so we still are at 3. And then we would say, what about every subarray starting at 3? Well, 3 and 4 is, the GCD is 1, but the length of this subarray is 2. So with this in mind, we can just say, okay, well, the minimum length subarray we found is 2. So with that in mind, there's one operation we can make that will get a 1 at all. And then once we have a 1, then we're like, okay, just like it's the length of nums minus 1. So that's one operation to get a 1, and then 3 operations to change everything else to be a 1. And that's kind of the crux of this code. So if we go through the code, we say, okay, just immediately check for 1s, sure. And then say, I'm doing like a 2-pointer approach. So I say, for I in range n, x is nums I. And then I look at every subarray I could construct starting at I. I might have wanted to change these to L and R, but whatever. And then I say, all right, if the GCD so far is 1, then we found our min so far. Otherwise, do a rolling GCD. And then in the end, I just say, and like, what was the minimum thing we found? And it's just going to be length of nums minus 1 plus that, because this is the minimum amount of steps we can use to set something to be 1. So then it's just going to be that plus the number of other elements other than that 1 that we've created. And if we can't do that, if nothing is relatively prime to anything else, or like if everything shares some sort of non-1 common factor, then we never set MSF to be anything, and we can return -1. And this one, I banged this out fairly quickly, and then I spent quite a while worrying about getting another bug because my previous bug was so stupid, and it cost me 5 minutes. So the lesson for me to have learned here was trust your code a little more. And I think the lesson probably for others to learn, if I'm like professing something, is like, 1, Excalidraw is really useful. Just like if you're ever really stumped, just opening it up and typing out numbers like this is useful. And also thinking about these rules of like, what if I set something to 1? Do I always want to just return length of nums minus 1 plus that? Yes, you do. And so on. Like you can sort of construct these solutions deductively. This is certainly a deduction problem. And then the other thing, if I'm getting more specific beyond sort of like cognitive habits to be in, is also like, what I'm doing here is I'm taking like a prefix GCD. I'm taking like a rolling GCD along every possible subarray. And obviously knowing that you can do that given the constraints, like knowing that you can get away with that time complexity, that's useful. But also like thinking to do that, thinking to use some sort of prefix operation, that happens a lot with problems that are like dealing with subarrays like this. And I think specifically, I think it's commutative. Yeah. Specifically things like this with the commutative property, where like the GCD of 6 and 3, the GCD of that and 4 is going to be the same as the GCD of 3 and 4 with 6. Things that have that property often will have some sort of prefix quality to them in the solution. That's a very specific lesson to be learned about this problem. But yeah, overall it was a fun and satisfying contest, if not for the rate limiting stuff.